Hello everyone. My name is Alexey Soshin. Can you hear me well at the back? Yeah, perfect. This is Concurrent Design Patterns in Kotlin talk. So a little bit about me. I'm currently a staff engineer at Deliveroo, former software architect at Get, and I'm also author of hands-on design patterns with Kotlin book. I know this name of a book is a bit mouthful. But yeah. So, goals of this talk. First of all, get familiar with half a dozen of concurrent design patterns. Then discuss a bit how concurrency is solved in some other languages. And convince you that concurrency in Kotlin is awesome. A bit of an intro. So when I first started those talks about 2 years ago, they were received pretty well. But back then, most of the people that came to conferences and meetups were Java developers. And then when I showed them something like this, so instead of this horror, this is the implementation of a singleton in Java. You could have something like this. They were like, oh, that's a really nice language. Unless, of course, there were some Scala developers that came to my talks and then they would like shout at me, yeah, Dersky invented that like 10 years ago. You just stole that from us and stuff like that. Yeah. Any Scala developers here? Oh, okay, because Scala developers are a bit of a fun killer for Kotlin meetups. We already had that. So yeah. But nowadays, when I show you object singleton, it's obvious because probably most of you are Kotlin developers. And by the way, is there somebody that's not Kotlin developer? Because then okay, so a few. Because all of my examples will be given in Kotlin. I just need to understand how deep I need to explain that. So no cheap tricks for me anymore. I need to discuss something more advanced. And then what I decided is that let's discuss something less obvious, like concurrent design patterns instead of the regular one, the classical ones. But is there such a thing? Because there's this book, probably you're familiar with it, at least from the outside, and there is no such thing in this book as concurrent design patterns, so probably it doesn't exist, right? And so there are a few things you need to know about this book. Maybe you know them, maybe you're not. It was written in '92, and that's the only edition of this book. And if you've seen examples from this book written in C++, in Java, that's not from this book, actually. That's somebody else written them, because this book is in C++ and Smalltalk. And yeah, I read that, and it wasn't fun. And this book obviously doesn't contain all the design patterns in the world. So we'll discuss a few that's not in this book, but still design patterns, concurrent design patterns. So why do I speak about concurrency? First, it's a hot topic in the past 10 years. And the main reason for that is that we're reaching the limit of how fast our CPUs can get. So we try to add more cores, meaning more parallelism, but there's also a limit for that. And our solution for this is actually concurrency. So concurrency is a way to optimize our resources. And unlike some other problems, concurrency is hard to visualize. In usual design patterns, we have nice UMLs, if UMLs can be nice. Here we don't have them so much, but I'll try to visualize them anyway. And a few words about concurrency versus parallelism. So parallelism is doing many things at the same time. So I'm speaking, you're listening, we're two separate entities and we are doing things in parallel. And concurrency is doing something while you wait for something else. So, for example, our brains are not parallel, but they are concurrent. And we are switching between different tasks, creating the illusion that we're doing a few things at the same time, but we're actually not. It's only an illusion. And one example is driving and speaking over the phone. So you're not actually doing two things at the same time. And what I want you to take from this is concurrency is an illusion. So let's actually start with the design patterns. And first one, if most of you are Kotlin developers, you probably are familiar with the async function. And the question is this a design pattern? So if you worked with Kotlin and Coroutines, you're familiar with that. And it goes like this. For example, usually you'll have a function, and inside we invoke the async function, and we wrap some synchronous code. So in this example, probably it's Spring or something, because it's called service. And somewhere else in the code, you invoke this asynchronous function, then do a wait. So if it's a design pattern, it's quite easy to guess that this is a design pattern, because that's the name of my talk. But what's its name? And anybody want to guess? So Kotlin compiler actually and Kotlin ID actually give us a hint. And if we look at the signature, we see that async actually returns us something called deferred. And yeah, this design pattern that async implements called deferred value. And in other languages, it's also called future or promise. They are all implemented the same design pattern, deferred value. And any JavaScript developers in the room? So not once I heard that from JavaScript developers that design patterns are obsolete, only Java developers need them, and there are no design patterns in JavaScript, and we're doing fine. So there are design patterns in JavaScript, and we're using them every day. Maybe in some cases we just don't know that they are design patterns. And the question is now, is it related though to any classical design pattern, any design pattern out of the Gang of Four book? If we look at the beautiful ASCII art in the job documentation, we'll see this. And somebody in JetBrains worked very hard to generate this diagram, probably. Or maybe he just generated it. And it's a state. So job, deferred in Kotlin inherits from a job. And every job is actually a state machine. So it implements state design pattern. The interesting part, it implements it twice. So once it implements it for itself. So every job is a state machine with specified states. And then when you write a coroutine, the Kotlin compiler breaks your code into pieces and creates another state machine, which is a dynamic state machine for your code specifically. So it's an interesting implementation. OK, to our next design pattern. So coroutines make everything better. And let's take a look at the following code. So that's the reason I asked if there are many people that are not familiar with Kotlin, because I wrote that it's obvious. Maybe if you've never seen Kotlin, it's obviously not. This code prints numbers between 0 and 100,000. We launch it in a main function. We have the run blocking, so it won't exit early, and for other reasons. Then we generate 100,000 numbers, and for each number we launch a coroutine. And since coroutine, as you know, are concurrent, we'll see those numbers in random order, semi-random. Yeah, so let's try to switch to my IntelliJ. You don't need to see the actual code, like it's exactly the same. And I'll run it. So if you look at the output, the numbers are not random at all. And that's really weird. But if it wasn't weird, I probably wouldn't show it in my talk. And there is a reason. They are all ordered and not in semi-random order. Because if we look, if we dig deeper inside the code, we'll see this. And there is actually an event loop. Since we run this code from the main thread and used run blocking creates an event loop. And the event loop uses only a single thread. And this was popularized by JavaScript. And the reason it's so popular is that when you have a single thread, you have less concurrency problems. One thread, no concurrency. And sometimes that's good. And another interesting part is that if we dig even deeper, you actually can see I created there 100,000 coroutines, and you can see them all in the queue. So they're all waiting to be executed sequentially. Back to design patterns. Event loop is actually a design pattern, and its official name is reactor. As I said, it uses a single thread, meaning no concurrency issues, which is sometimes good. But the reason is, if something blocks the thread, the world stops. So I decided not to show that because it's a bit boring, like you won't see numbers for some time. And it's also pretty obvious at this point, I would say. But yeah, that's one of the problems with event loop design pattern. And Node.js runtime uses this model. So we discussed two of them, deferred value and now the reactor. What about this code? I'm not sure how well can you see it, but it's exactly the same code where I changed only one line, which says now that my launch will use dispatcher's default. And what do I say? Is it the same design pattern or not? And if I run it again, I should see the numbers are, I didn't run the correct one, I think. Yeah, let's see again. It should be random at this time at least. Yeah, that's better. So now the numbers are still pretty ordered. That's not what I wanted. But yeah, they should be more mixed at least. And the reason is that the dispatchers implement another design pattern. And that's the part where I'll try to visualize what's actually happening when you launch 100,000 on, in my case, 1,000 coroutines on a default dispatcher. Yeah. So what happens here? On my laptop, I have 8 cores. So we have actually each column is a single thread. And the green lines you see are the coroutines that I launch. So we'll run it again. And I launch them in a loop. As you've seen, it's exactly the same code. But notice a few interesting things. First, they are not distributed evenly. So some threads get more coroutines to execute, some threads get less. And another part is that even though some threads get more tasks to execute, they may finish before others with less tasks. So it's distributed in pretty random order, even though I have the same amount of work for each coroutine. And as you may have guessed from the name of the file that I executed now, it's called Multi-Reactor Design Pattern. I think it was coined about 10 years ago by Vertex framework, which is a Java framework. And the inventor of Vertex, which is a British guy, Tim Fox, he looked at Node.js at that time. It was 2010. And he said to himself, wait, but Node.js is actually an event loop written in C++. I can do the same in Java, and I could use more threads, and it would be even better. So that's how he invented the multi-reactor design pattern. And its benefit, it uses all the available CPU cores. So as you've seen, I had 8 CPU cores, so my coroutines are spread evenly. Are spread across all cores, but they are not spread evenly. And Go language uses this model for Go routines. So if you heard about Go routines in Go, they are just coroutines, very similar to what Kotlin does. A bit more help from the compiler because they have only one concurrency model, so they could optimize it a bit more. OK. So let's see another example. As I said, I'm from Deliveroo, so everything will be around deliveries and drivers and stuff. Let's see, we want to fetch the profile of our driver. So we have this data class with a picture, some of his favorites and friends. And then we fetch some elements. And the problem is, if I run this code, let's say this is written in Ruby, and each endpoint is 100 milliseconds, 200 milliseconds, and 300 milliseconds, respectively. If I run this code, it will take me 600 milliseconds. And that's the same like if I go back a few years ago and would use Spring MVC or something like that. So what we do in Kotlin, we usually wrap all those functions in async blocks. We use basically the same data class. And then you use await. So you have this data class underneath. And you use await on all the elements. And hopefully it will be more concurrent and faster. So this example will take half of the time. And my usual question is this a design pattern? Because it looks quite naive, I would say. But yes, it is. It's called a barrier. And it makes sure that coroutines can proceed only when they all reach the same point. So if we go back, the point when we return the object is the point where all the other coroutines can proceed. So sometimes here it's an object that you would have created anyway, like this function obviously returns the profile. But in some other cases, you may have created this data class only for the purpose of synchronizing all of your coroutines. Now, some more examples. Let's say I have a web page, lolcats, and I would like to fetch all the images from it. So what do? You decide to do that in Kotlin, so you do something like this. You have this produce function, which creates us a coroutine and binds it to a channel. So we return scrap gets an URL and returns a received channel. Let's say it's a channel of strings. And then inside the coroutine, you fetch HTML. You parse it, so you get all the links from it. And then you start sending the links over the channel for somebody else to consume. And what design pattern is this? So you probably wrote something like this if you use Kotlin. And it's actually called actor. It has two goals: to encapsulate concurrency on one hand, so that's what Coroutine does in our case. And it communicates using message queues. So our channel is a message queue in this case. In some languages and some documentation, you may see that message queues are called mailboxes. And often you'll have two mailboxes per actor, so one for incoming messages and one for outgoing messages. But it's not mandatory. As long as you have some kind of coroutine and at least one channel, you implemented an actor. This model was popularized by Erlang in 90s. Also, Akka framework from Scala uses this model. And it's pretty successful. So the accompanying function to produce is actually called actor. And I think about a month or two ago, there was a discussion on Kotlin forums about whether it should be called an actor, because if it's an actor, it's very lightweight actor. But Roman Elizarov said, yeah, probably it's still an actor. OK, let's continue with our example. So we produce these images, those links. We send them over the channel. What do we do next? So we could, of course, download them one by one. But hey, we're not in Ruby to do that, right? We have Kotlin at least. So we would like to spawn a few downloaders instead of one. And then each downloader gets the same channel. Actually, it could be done a bit simpler. I did it because in the real code, it's a bit more complicated. It has two channels. But in this example, it has only inbound channel. And then we start each downloader. Each downloader waits on the channel. If you have like 8 CPUs, we can launch 8 downloaders, for example. Only one of the downloaders wins every time, so message arrives to only one, and then it starts downloading the image. So it's called a fan-out. When I distribute this work, when I have single channel and I distribute work across a few actors, it's a fan-out. And it has two main benefits. One is it's very scalable. So as I said, if I have 8 CPUs, I can create 8 actors, or maybe I decide to create 16. Or if for some reason I want to reduce the load, I can just reduce the amount of actors, and it will all be done in runtime. We're continuing. So we got those links. We download the images. And now we need to store them to disk. So of course, we can decide that each of our downloaders also can write to disk. Technically, it's possible. But it's not really a clean code. It's not really a good separation of concerns. So it would be more effective if we'll have only one or only a few of them that would write to disk. So what do? We create, this time we can use actually the actor function, which receives some kind of messages. So in this case, it doesn't make sense to send anonymous bytes arrays. So we'll send some data class with byte array and its name, and it will just wait on the channel and gather all the results. So we'll go back to our code. And that's what it looks like. So I must say that when I showed you the multi-reactor design pattern, I cheated a bit. I recorded the results ahead of time, and then I just visualized them in JavaScript. This actually runs in real time, so I'm pretty scared because it may get stuck. And what happens here is all the code I showed you about the downloaders and other actors, it actually runs now. And each time I send a message over a channel, I duplicate it, and I send it over a WebSocket to UI. So this is all happens in real time. We have the HTML fetcher that fetches all the links. And then, because I have 8 CPUs, so I decided to create 8 image fetchers, downloaders. And then they are sending their results, the downloaded images, to a single image saver. You can see the counts. You can see that downloading, getting the links, distributing them is very fast. Actually, I had to slow it down because otherwise it would finish in a few seconds. And downloading the images was, of course, much, much slower. So yeah, I try to visualize that. And from here, you also can see where the names are coming from. Because this is fan out, and the lower part is actually fan in. So we have spreading and gathering again. So in concurrent design patterns, it's called fan in, fan out. In other places, you may hear of that as map reduce or divide and conquer. It's all the same principle. So we've seen what it looks like. And as I said, it's called the fan in design pattern. Allows to gather results from multiple sources. And its advantage is that it decoupled from producers. So if we can add more actors or reduce the number of actors in the fan-out design pattern, so fan-in also supports that. So I could have only 2 producers, and it will still work. Now, my animation is a bit wrong. I'll go back to it. Because it may seem that I have 16 channels, 8 incoming channels and 8 outgoing channels, and that's not the case. I actually have only 2. So let's try to see that. Yeah. And that's what it actually looks like. So I have one channel to send those links. And I have another channel to communicate with the image saver. And again, you can see the timings that downloading the images takes much more time. All those examples are available, so you can run them later. OK. So to summarize, design patterns are everywhere, even though you may be not aware of them. They are not limited to the Django 4 book. Different programming languages use different concurrency models. But the awesome part of Kotlin that it incorporates different concurrency models in the same language. So we've seen event loop, we've seen multi-reactor, we've seen actors, and it's all in the same language. It's flexible enough so you could choose what's the best tool for your case. A bit of references. So if you're interested in classical design patterns, those are 2 great books. Let's put it like that. Design patterns, the classical one, it's pretty hard to read nowadays. Head First Design Patterns is totally awesome. And there's also my book. It has 1 or 2 chapters about specifically concurrent design patterns in Kotlin. So thank you very much. That's the link to the concurrency examples which you can run. Now I must say that Kotlin code is pretty good. Don't look too much into JavaScript code because it's vanilla JavaScript, and I'm not a very proficient JavaScript developer. And if you like to keep in touch, there's my Twitter link, Stack Overflow, and GitHub. So thank you very much. If you have any questions, just feel free to catch me later. Thank you.